So you can see in the upper right of that little window, when I move the flashlight, you can see everything moves. All right, everyone, today we're going to be making a spectrometer or spectrophotometer or optical spectrum analyzer, whatever you want to call it. We're going to need a few things. The first thing we're going to need is just a USB camera. This one happens to be a microscope. It's kind of a crappy microscope, so we're just going to be using this in this project. The second thing is we're going to need our Comic Sans Super Learning Kit, and I'll show you why. Okay, we're gonna open this up. You know, you got all your little tools in there. Yeah, you can have a lot of fun with this. Oh, what's this? You got a CD. Let's open this CD real quick. All right, cool. Laughing, that's funny. It's like laughing. It's okay. Okay, so what we're gonna do is we're just gonna break that into a million pieces, because what we need from this is the diffraction grating. So right now you're seeing a reflection of me. But if you see right there, you see that little rainbow right there? That's how we're going to actually split our light source into a spectra in order to analyze what spectra is absorbed or reflected or refracted through our material that we're measuring. So I'm going to clean up the mess that I made just now. Hopefully I don't step on anything, but we're going to delaminate somehow. We're going to separate the layers of the CD to get this diffraction grating. Now you can buy diffraction grating from Jeff Bezos. You want 1,000 lines per millimeter, apparently. That's what Thought Emporium said. There's a lot of other videos on this. Thought Emporium is a good channel. Okay, so I meant to say that someone on Reddit suggested this when I posted my tubular fungi reactor video. I just want to give him credit. I'll put a name on the screen or something. He sort of gave me this idea. He or she, they, them, whatever you want to be called, mister, or I did it again. Okay. Basically, I can just take off this clear plastic piece, you know, cut out a piece of diffraction grating that fit, shoved it in there, turned off that LED ring because we're going to be looking at light, so we don't need to be producing any light. So this is what I'm going to do. Okay, so I have these fancy RGB lights in my computer. Rate my setup. And then this is just plugged in with USB into my computer. This is super meta. We're looking at itself. I'm going to point this at one of the RGB LEDs, and we're going to look on the screen and see what happens. Okay, so we're on one of the RGB LEDs, and you can see right there we're getting some artifact going on. Now, normally when you're taking a picture, you don't want to see things like this, but in this case, I'm super happy because that means our diffraction grating is doing something. You can see it's actually splitting up the light into red, green, and blue. You can actually see the red, green, and blue there. That's really, really cool. So the reason that you don't see the LED as red, green, and blue directly due to the diffraction grating is because of how the incident light and how the angles work. So when we actually go to set up this spectrometer, spectrophotometer, whatever you want to call it, we actually have to have the camera at a 30-degree angle. So looking at the top of the box, what we're going to have is, you know, at a 30-degree angle, we're going to have the camera looking at the side of the box. We're going to have a thin slit here, probably made with razor blades, just to have a really precise slit. And then at first we'll probably won't have a cuvette here. Cuvettes are kind of expensive. I might find some cheaper ones. But everything I'm using right now is just around the house. I'm going to 3D print a really simple box. I'm just going to use Tinkercad. Okay, so here is the 3D printed case. Look, it says Spectrophotometer. Sorry, my hands have paint on them. I didn't wear gloves. It's got the slot for this microscope camera. It's got a slit here, and then it has a slot for a cuvette. So I ordered a couple of quartz cuvettes online. And then I planned on using these screws here. I think I got the countersinks pretty close. I haven't screwed it together yet, but the hole sizes are right. So I'll include the Thingiverse files in the link below if you want to print this yourself. Okay, so we finally have something that sort of works. You can see the little rainbow peeking in there. So what I ended up doing is taking off that plastic cover and putting a section of this diffraction grating that I got from the CD on top of that little LED circle here. I'll show you. So you can see I just have a those LEDs aren't on in there, it's just a flashlight. I have a piece of tape holding on a piece of this diffraction grating over the lens, and I have it zoomed all the way in on the microscope, and I'm still not really getting a large spectra, but you can see that we get some blue and we get some red. You know, since I took out the IR filter, we can go to the infrared spectrum if we want to. Okay, I moved the monitor off of the top of my desktop so you guys can see this. So some of the things that we can adjust here are the height of the light, and we can adjust the angle of the camera. First, if we adjust the height of the light, you can see our image will focus up or down. So moving the light higher goes up, and moving the light lower goes down. That's pretty straightforward. The second parameter that we can adjust right now is we can adjust the hangulation of the camera. So I'm going to do that now. I'm twisting it this way, and we're getting more into the red spectra. And then if I twist it the other way, we'll get back towards the blues and the greens. Okay, so it doesn't really have very much range of motion, but at least we'll get some sort of an image. Another thing that I think is interesting with this setup is, since it is a microscope, we're essentially zoomed in on a region of the spectra. So all of the DIY spectrometers that I've seen, you know, either use one wavelength in particular with a sensor that only senses that wavelength, or they use a camera that sees, you know, all visible wavelengths. So what's interesting about this is we can get more resolution in a particular wavelength range, rather than going all the way specific on one wavelength or all the way general with a normal camera sensor. I can pretend this is by design, but it definitely isn't. You know, I just had this microscope camera laying around. Yeah, you can see I took it apart and put it back together. Yeah, there wasn't a reason to take it apart besides taking off the lens to get out the IR filter, but whatever. Okay, so getting the software set up was actually a lot easier than I anticipated. So you can see in the upper right of that little window, when I move the flashlight, you can see everything moves. Awesome. Yeah, that was way easier than I expected. So there's a built-in calibration there. So the exact wavelengths might be a little off, meaning the colors might be a little off. But yeah, okay, in my hand I've got this methylene blue solution. It's dilute, of course. I don't have my quartz cuvette in. I'm still sad about that. It'll come eventually. So I'm gonna plop this in and see what happens. That's pretty cool. Okay, I have no clue if this is going to work, but you can see here at 458 nanometers, we're getting 97%. You might not be able to see that. And then if I take the sample out, that region goes down, while at the same time, the region at 700 nanometers stays constant. I'm going to try to use this region of the graph as the quantification of the dye. So I'm going to go through all the samples, including the water and the broth and the effluent of the tubular flow reactor, and see how much dye is in each sample. Okay, so what I've done is I've gone through and I've done all of the calibration samples. You can see the results here. And my natural instinct is to type data into Excel, and so I generated this graph here. You can see there's a bit of a logarithmic shape to it. These lower values, which were the water all the way up to the 0.05% sample, were not very good, and they basically just read 0. As you get up to 0.5 and above, they're all going to read about the same value at this 100%. You can't see that, but 97% and then 100%. Can't really tell the difference between those two. But in between here, which is the 0.1 and the 0.5, we have plenty of room to actually do calculations, and this region of the graph is likely linear. So typically when you're working with sensors or anything like that, you're going to have logarithmic data. However, there'll be a region of the graph where, even though it is logarithmic, it's linear in that region. It's logarithmic overall, but linear in that region. And typically sensors like to work in that linear range because that's where they have the greatest accuracy. So we might end up working outside of that range today. I'm going to go ahead and test our experimental samples. I'm interested to see if we have any peaks in any other areas as well, and if we have any peaks at this 458 nanometer mark that might fall on this graph. Okay, so this is the broth. And we're getting 89% at our 458 nanometer range, which is within our linear sensing capability. So this is the 3-hour recycle sample. And we're actually getting a much higher value than our original sample. And this might be because there's other contaminants in the broth, and maybe the wavelength that we've chosen is not very selective. We essentially might just be measuring the opacity of the sample rather than the presence or absence of this compound. This is the 10-hour recycle. We'll see what the mycelia does. Essentially at this wavelength, too much of the light is being blocked for us to actually determine anything useful. Okay, some of those samples really smell terrible. They've been sitting for a while, like a month now, so that's probably not good for my health. But I think what we've done here is essentially created an optical density spectrometer, and these are really useful in lab as well. They essentially give you an idea of how many cells are in solution or how much of an opaque compound is in solution. So this is really useful. I think this spectrometer might need more dialing in if I want to measure more different compounds. A few of the improvements that I definitely want to make is, first, I want to swap out this microscope for something else. I think it's interesting to be able to zoom in to a certain spectra that we're seeing, but I think for initial prototypes, it's best to be able to see the entire spectra. I think this box is actually pretty good. You know, the cuvettes fit well in it. The cuvettes work really well. This light source is working well. I think the main thing I want to change is just the camera. Behind the camera, the next thing that I would want to change is the diffraction grating. So I'm using a diffraction grating that I pulled from a CD, and I think using a purpose-built diffraction grating at 1,000 lines per millimeter or whatever the number is might actually be better and give better data as well. So overall, what I think we found here is that it is possible to build a spectrometer essentially with things you already have laying around your house, and the spectrometer will be about as useful as the parts that you throw at it. If you want to build this yourself, I'll put the Thingiverse links to the 3D file in the description below. I'll also put a link to this software if you want to download it. It's super good, it's super useful. I couldn't have done this project without it, to be honest. And if you have any suggestions or comments or recommendations to make this setup even better, please let me know down below. Anyway, thank you for watching. I'll see you in the next one.